All right, David Lazar is going to talk about private messaging.
Hi, my name is David Lazar. I'm a PhD student at MIT, and I'm going to present Vuvuzela, a scalable private messaging system. The motivation of our work is that we would like our communication to be private. For example, if we're talking to an oncologist. We can encrypt the contents of our message, but just the fact that Alice is talking to an oncologist already reveals a lot about her. A more powerful adversary that has access to even more metadata can learn a lot about Alice and Bob. For example, the adversary sees that Bob is talking to AA and might be able to infer that Bob is an alcoholic. The adversary also sees that Alice is talking to a lawyer and the press and can infer that Alice is suing Bob for malpractice. Furthermore, the NSA, an ex-NSA official recently said, "We kill people based on metadata." So metadata is an important problem. The goal of this work is to build a messaging system that hides the metadata. Namely, users should be able to talk to each other without revealing who's talking to who. We want this system to continue to hide the metadata, even if most of the servers that power the system are compromised by the NSA. And here, the little computers with little androids in them represent servers that are compromised. Our second goal is that we want this system to scale to millions of users. I'm only going to use a messaging system if my friends are on it, and my friends are only going to use it if their friends are on it. So overall, the system needs to support a lot of users. Unfortunately, no system today achieves both of these goals of privacy and scalability. For example, we might think, well, we could just talk through Tor. Unfortunately, every year there's a new paper that says how we can break Tor's privacy. So recently, people have tried to build systems that provide strong privacy guarantees. For example, Riposte and Dissent both give very strong privacy guarantees, but they can't actually scale in the same way Tor does. Our contribution is Vuvuzela, a system that achieves strong privacy with good scalability. And we do this by using a slightly weaker form of privacy known as differential privacy compared to cryptographic privacy that Riposte and Dissent use. In particular, the contribution of our work is Vuvuzela, the first private messaging system that hides metadata from powerful adversaries for millions of users. Vuvuzela scales linearly with the number of users, and it provides differential privacy for millions of messages per user for 1 million users. Under one configuration, it has 37 seconds of end-to-end message latency and 60,000 messages per second of throughput. We believe these numbers make Vuvuzela a good match for private text-based messaging. So what does Vuvuzela actually look like? So Vuvuzela is composed of a handful of servers arranged in a chain. Users send and receive messages through the first server, which then passes them on to the next server, and so on, until the messages reach the last server. The last server decides who gets what messages and that sends them back down the chain. So Vuvuzela is actually composed of two protocols, the dialing protocol and the conversation protocol. The dialing protocol is used to initiate conversation sessions between two users, and the conversation protocol is what users use to actually exchange messages. In this talk, we only focus on the conversation protocol, and we leave the dialing protocol to the paper. We assume that Alice and Bob want to talk to each other, and that they've already gone through the dialing protocol. Vuvuzela's threat model is as follows. We assume that all but one server are compromised. The adversary may be active, meaning that the adversary can knock users offline, tamper with messages, etc. All users that are connected to Vuvuzela might be malicious, besides you and your friends. And we also assume public key infrastructure, so that users are able to get each other's keys. So given this threat model, what are we trying to achieve? Here we have three scenarios, the different scenarios that Alice can be in. In scenario 1, Alice can be talking through Bob through Vuvuzela. In scenario 2, Alice is talking to nobody. And in scenario 3, Alice is talking to Charlie. What we want is for an adversary to not know which scenario we're currently in, despite any observations it might make. For example, it might try to compromise servers or perform traffic analysis attacks, but it still shouldn't know which scenario is actually happening. Namely, it shouldn't know who Alice is talking to. So how do we achieve this goal in a scalable way? We'll use efficient cryptography to encrypt as much metadata as possible. Then we'll add noise to any metadata that we can't encrypt. Then we'll use differential privacy to reason about how much noise we need to add, or how much privacy the noise gives us. So let's see how we apply this approach in Vuvuzela. So at the core of Vuvuzela's design is this idea of dead drops. We don't actually want users to communicate directly with each other because this would reveal metadata. So instead, they'll communicate through dead drops. A dead drop is a place where a user can leave a message that another user can pick up. So how do users chat through dead drops? Suppose Alice and Bob want to talk to each other. They'll both agree on a random dead drop to use, and then they'll both send a message to this dead drop. When the server encounters two messages to the same dead drop, it simply swaps them and sends them back to the users. And this way, Alice and Bob get each other's messages. Of course, in order to have a conversation, Alice and Bob want to send multiple messages to each other. So the system operates in rounds. So in the first round, perhaps Alice sent a message, but Bob didn't actually have a message to send this round, so he'll send an empty message just so he can get back Alice's a message. But in the next round, Bob might reply, so they'll agree on another random mailbox to use, and then Bob will send his message, and then the protocol will continue like this for the lifetime of their conversation. Of course, the messages are encrypted, so they don't reveal anything to the adversary. And the dead drops are also long pseudo-random strings, meaning two things. They don't reveal any metadata, and users will never collide on the same dead drop, unless they know the shared secret that was used to establish, to agree on these dead drop IDs. Finally, the adversary that's looking at this picture can see that Charlie is not talking, and this reveals metadata. So what we'll do is we'll also have Charlie send messages to random dead drops, even though he's not in a conversation. So I claim this already gives us pretty good privacy. If the adversary only sees the left-hand side of this image, it only knows who's connected to the system, but we're fine with leaking that information. And if the adversary only sees the right-hand side of this information, the adversary sees that people are accessing these dead drops, but it still doesn't know what's going on. So how can we enforce that the adversary never sees both halves of this image at the same time? We'll use a Mixnet. So the Mixnet will hide the origin of incoming messages. So we'll have the last server actually manage the dead drops, and the users, instead of talking directly to the server hosting these dead drops, it'll talk through the chain of servers, and the chain will obscure the origin of these messages. So how does this work? Suppose messages A, B, and C are Alice's, Bob's, and Charlie's messages. They'll get sent through to the first server. The first server will then shuffle these messages, send them on to the next server. The second server will shuffle them and then send them on to the final server. As long as one of these servers is honest, it won't reveal its shuffle, and then the last server won't actually know where these messages came from. So are we done yet? Unfortunately, no. There's still one last subtle piece of metadata. Namely, the last server sees that there's a dead drop with two access counts, so it knows that somebody is talking. So is this actually a problem? Well, let's do a demo and see why it is. All right, so here I have 3 terminals. In the top 2 terminals, I have 2 Vuvuzela clients, the one on the left belonging to Alice and the one on the right belonging to Bob. In the bottom half, half of the window, we have this third terminal, which is running the Vuvuzela protocol that we just saw. In the top half of this terminal, we see the number of dead drops with one axis in this little graph. And in the bottom half, we see the number of dead drops with 2 axes. And we can see that since Alice and Bob are connected to the system, there's already dead drops with one axis because they're sending cover traffic. So let's see what happens as soon as they start talking to each other. So pay attention to the bottom terminal. So we'll have Alice talk to Bob, and Bob talk to Alice. Right, so suddenly, the state on the last server changed. Namely, now there's a dead drop with 2 axes, and the server knows that somebody is talking. Now, if the server suspects that it might be Alice that's talking, what they can do is they can knock Alice offline because they're an active adversary, and then see if the number of dead drops with 2 axes changes. So let's kill Alice's client and see what happens. And of course, immediately, the number of dead drops with 2 axes went to 0, and then now the adversary knows that Alice was talking. And this violates privacy. So how do we fix this problem? Our solution is to have each server add noise. We can't really encrypt these access counts because the last server needs to know which dead drops are being accessed in order to exchange messages. So instead, the previous servers will add noise to kind of obscure the meaning of these access counts. So we'll need to add two forms of noise that generates dead drops with two accesses, and noise that generates dead drops with one access. So what does this noise actually look like? Well, we have fake singles, which is a random message to a random dead drop, and fake doubles, which is two messages to the same dead drop. So now let's see why this noise is effective. All right, here we have the Vuvuzela protocol running with noise. And this is the same setup as before. We have the two terminals at the top running Alice's client and Bob's client. But now the last server is also has a bunch of accesses already that's due to all the noise that's coming from the previous servers. So let's see what happens when Alice and Bob start talking. All right, now the adversary has a much harder time figuring out what's going on. In particular, it can't really tell if Alice and Bob started talking or not, because a dead drop with two accesses could have been generated by noise. And let's see what happens if the adversary tries the same attack as before. Suppose the adversary thinks that Alice might be talking, so he'll knock Alice offline and see how things change. All right, and so it seems like we can't actually tell what's going on from this graph. So how can we actually reason about why this is secure? To reason about why this is secure, we're going to formalize our privacy guarantee using differential privacy. This is what differential privacy tells us. Suppose we have some observation from the terminal, as seen here, and let's call this observation I. What differential privacy tells us is that the probability of having made this observation I, given Alice did talk to Bob through Vuvuzela, should be roughly equal to the probability of having made the same observation given Alice did not talk to Bob through Vuvuzela. In other words, the adversary can see this observation, and it shouldn't be able to tell which world he's in, whether Alice is talking to Bob or not. More precisely, we use a form of differential privacy known as epsilon delta differential privacy, which we've simplified here for the purpose of this talk. What this definition says is that these two probability distributions should be within a factor of epsilon of each other. As epsilon approaches 1, these distributions get closer and closer together, which means better privacy. So why does adding noise even achieve differential privacy? Let's look at why using a simple example. Let D be the number of dead drops with two accesses in a single round. To make D differentially private, we need to make the following two distributions very close together, or indistinguishable. The probability of D equaling some value given Alice talked to Bob through Vuvuzela, and the probability of D equaling some value given Alice did not talk to Bob through Vuvuzela. On the left-hand side of the screen, we see these two distributions plotted without any noise. So D is either equal to 0 if Alice did not talk to Bob, or D equals 1 if Alice did talk to Bob. So these probability distributions are trivially distinguishable. What we'd like is for these distributions to look like what's on the right-hand side of the screen, namely these two distributions are very close together. So how do we actually generate these, how do we add noise so that these distributions are actually close together, making them indistinguishable? Well, we have a few constraints. First, we can't have negative dead drops because we can't add negative messages. The only thing we can do in terms of noise is add messages. And these distributions have to be close enough for differential privacy. What this ultimately means is that we have to add a surprising amount of noise. For example, just to obscure this one variable for one round, the average amount of noise we need to add is on the order of hundreds of messages. An additional challenge to adding noise is that privacy degrades every round. Every round leaks metadata, because the adversary will see the dead drop access counts across many rounds and might be able to infer patterns after making observations over a long period of time. So what we actually want is we want differential privacy to hold after sending many messages. This means adding more noise to support more messages. And since adding more noise means more privacy, Vuvuzela will add as much noise as possible while still keeping the system practical. Then we'll use differential privacy to compute how much privacy users get given our level of noise. And we do this using a composition theorem from differential privacy, and you can read about this more in other papers. For the rest of this talk, we focus on one level of noise, namely 300,000 fake singles, and 300,000 fake doubles added per server per round on average. So what does adding this much noise buy us? Well, recall the formula we just saw. And here we have a graph with epsilon on the y-axis and the number of messages Alice wants to keep private on the x-axis. Remember, as epsilon is close to 1, we get more and more privacy. And here we can see Alice can send millions of messages, and epsilon is still pretty small. However, if Alice wants to send more than 2 million messages, then epsilon grows very quickly, and then she starts to lose privacy. But what do these numbers actually mean? So let's do a hypothetical experiment here. Suppose that Eve is very evil, and that Alice wants to send messages to Eve. So Alice sees the previous graph and decides to send Eve many messages through Vuvuzela. Will the NSA arrest Alice for talking to Eve? The answer is probably, because using Vuvuzela is already pretty suspicious. So then the question we should ask is, will a fair jury convict Alice of talking to Eve? The answer here is that it's unlikely. Vuvuzela observations are not damning evidence. To see why, let's suppose that the jury is already 50% certain that Alice did the crime. And this could be for a variety of reasons. Maybe the NSA is intimidating or has presented other evidence. And let's also suppose that Alice is getting a fair trial, so she'll only be convicted if the jury is certain beyond unreasonable doubt, which in this case means 90% certain. So here we have the same graph as before, except we've replaced the y-axis with the jury certainty. So we can see if Alice only sends on the order of 10,000 messages to Eve, then the jury certainty doesn't go up at all. It stays at the previous 50%. When Alice can still send millions of messages to Eve without actually going to jail, though. As soon as she sends more than 2 million messages, though, then she should be worried. So we implemented Vuvuzela in Go, and it ended up being around 3,000 lines of code. An interesting note about our implementation is that it uses an untrusted entry server to manage the user connections. So we wanted to keep the servers that do the cryptography and the noise as simple as possible, so we separated out these two concerns. The entry server notifies clients when a new round starts, so the clients don't actually need to be in sync. And the code will be available soon on GitHub. In our evaluation, we wanted to answer two questions. Can Vuvuzela servers support a large number of users and messages? And does Vuvuzela provide acceptable performance? Let's first start by reasoning about Vuvuzela's asymptotic performance. Well, the noise that we have to add is independent of the number of users. And this is great for us. That means that the performance is linear in the number of users. And we can make various trade-offs about bandwidth, latency, and CPU. In evaluating Vuvuzela's performance, we used a bunch of Amazon EC2 VMs. Each VM was running with 36 cores, and there were 10 gigabit links between the cores. We used 3 virtual machines for the 3 Vuvuzela servers, 1 virtual machine for the entry server, and 3 additional virtual machines to simulate clients. This graph shows the end-to-end latency for text messaging. So on the x-axis, we have the number of users that are online and sending messages through the system. And on the y-axis, we have the end-to-end latency for conversation messages. So we can see that with 1 million users connected, Vuvuzela provides 37 seconds of end-to-end latency. We can also see that this scales linearly. It's interesting to note that with only few users connected, the latency is 20 seconds, which means that just the noise alone is generating about 20 seconds worth of latency. So what are the performance bottlenecks in Vuvuzela? Well, Vuvuzela is CPU bound, and the CPU cost is dominated by the Mixnet operations. Vuvuzela also has a high bandwidth cost. On average, the bandwidth for servers is 166 megabytes per second and 12 kilobytes per second for clients. The 12 kilobytes per second for clients is mostly due to the dialing protocol, which we haven't talked about here. We can lower the bandwidth costs by increasing latency linearly. In conclusion, the problem we were trying to solve is to hide metadata in a secure and scalable way. Our approach was to encrypt as much metadata as possible and to add noise to obscure any remaining metadata. We formalized our privacy guarantee using differential privacy. We built Vuvuzela, which is a scalable private messaging system that hides metadata. It scales linearly with the number of users, and provides privacy for millions of messages per user with 37 seconds of end-to-end latency and 60,000 messages per second of throughput. Thanks.
Hi, Cheng Tan from NYU. So very nice talk. I have a little question.
Yeah.
So what's the difference between your protocol and the following simple protocol, which is there is one central trusted node, and every client will send to that central node per round a message. Empty means he doesn't want to talk, and that central node will reply in that round. So notice that the central client can be extended to the all but one flavor cluster or chaining as you described.
Right, so we don't want one central trusted server because who's going to run that server in a way that people will trust. So we have a better assumption here, which is that if we can have as many Vuvuzela servers as we want, and as long as one of these servers is uncompromised, then we'll get security.
Yeah, I said that's one. I mean, in that simple protocol, that one server can be extended to the all but one flavor chaining as you described. But I think my question is, what if every client will send a message to the Vuvuzela server each round?
Yeah.
Is there any difference between your differential privacy? You will send, I think, 300,000 message per round as a noise.
Yeah.
But actually, if you support 1 million client, basically, if everyone sends a message, that's only 1 million, compared with 300,000.
Right. So it would be excellent if there are 1 million users connected to the system. That is already in some sense noise. So there's some work in differential privacy about how we can reason about these kind of things. But we took kind of a very pessimistic view where we assumed that all users might be malicious. So we didn't want to assume that there might be honest users actually contributing to the noise. But you're right. I mean, in future work we can maybe tackle this problem or we might be able to reduce the noise by assuming that the users themselves act as noise.
Okay, thank you.
Yeah.
Hi, John Howell, Google. So it seems that you basically have to generate noise, fresh noise for each user. Like you're not taking advantage of the fact that all of these users are interacting in the same network. Is there some way to reduce the overall overhead by aliasing the Dropboxes together in some way so that some legitimate communicators are providing cover for other legitimate communicators?
But, so I think that's the same question as before. So it would be awesome if we could use the honest users as noise, but we haven't done that in this paper. I mean, I think the analysis becomes a little bit more tricky to do that.
Thanks. Sebastian Angel from UT Austin and NYU. So from your description, it seems that you're arranging the servers in a chain, and furthermore, each server needs to process not only the requests sent by the users, but also the noise added by previous servers in the chain. So in what sense is Vuvuzela actually scalable? Because it seems that adding more servers actually decreases the number of users that you can handle.
Right, so if we want to add more servers, everything, will decrease linearly.
Okay, so how would you go about scaling the system? Or is there no way to add hardware to scale the system?
So you mean, okay, well, to support more users, adding more servers in this configuration is not necessarily going to support more users. We would add more servers to, for example, reduce our trust assumptions. So if in the future, it would be interesting to build a more distributed version of the protocol where we could continue to add as many servers as we can to the network, similar to the way Tor works, and then distribute the load among all of these servers. But yeah, in Vuvuzela's case, if we add more servers, the latency will go up.
Okay, thank you.
Yeah.
Hi, I'm Stephen Sherritt from Data61, formerly Nicta. My question is, so kind of related to the last question where all your servers are arranged in a chain, what happens if one of the servers goes down in the chain? Do you have a single point of failure?
Right, so we don't actually try and prevent denial of service attacks. So if one server does go down, then people won't be able to send messages. And we can try and tackle that in future work, but we haven't done that here.
Thanks.
Yeah.
Anandjai, Yale University. So how did you attack the malicious server? So if I'm a malicious server, I can, add anything, and I can add, I can reject, decrypting, the message, and I can do a lot of, arbitrary things. So I guess you're using the Mixnet. So, but in the Vuvuzela, how did you, detect the malicious server, and how you kick them out?
So if at least one of these servers is honest, then it'll add, so we have each server add the maximum amount of noise that's necessary to provide differential privacy. So if the malicious servers don't actually follow the protocol, for example, by not adding noise, then the users still get differential privacy because at least one server has added the correct amount of noise. And then the antitrust the antitrust assumption in terms of a Mixnet is a standard antitrust, is a standard assumption with Mixnet. So as long as one of these servers is honest, it won't reveal its shuffle, and the rest of the servers won't know where the messages came from.
Right, but when I run the shuffle, I may dishonestly run the shuffle, right? So how you verify my shuffle operation or the operation is correct or not? Right. Maybe we can talk that offline.
Well, we just assume that there is one uncompromised server. We have no idea to tell which one it is or if one actually exists, but we just assume that there is one. So if we did want to, reduce this assumption, we should add a bunch more servers so that at least one of these is uncompromised.
Okay. Thank you.
Yeah.
You've talked about the noise generator, but is it really a random noise generator, or it is a pseudo-random noise generator that's really got a random number generator inside, somebody can have access to the code?
So we take all of our randomness from dev urandom. So you can interpret that however you want. I guess it is a pseudo-random number generator, but it's being fed with some real entropy. So I don't know if that answers the question. Yeah.
There was something I didn't, David Gill from Salesforce.
I can't really hear you.
David Gill from Salesforce. There was something I really didn't understand, which is why the same rendezvous ID or the same mailbox ID or whatever you're calling it is used for both sides of the conversation, right? Because you could just hash Alice to Bob communications with 1 bit appended at the end, and Bob to Alice with a 0 bit appended at the end from your Diffie-Hellman shared secret, and get 2 mailbox IDs, and those will always have one message rather than having 2 versus 1.
That's roughly what we do. So to derive the dead drop IDs, we basically hash their shared secret with the round number, and that's how they agree on dead drops. I don't think I'm understanding what you're proposing, but.
Okay, so Alice to Bob messages and Bob to Alice messages have the same dead drop ID.
Yeah.
Why don't they have different dead drop IDs?
Well, then they wouldn't get each other's messages. So the server will.
If they know them deterministically, or what am I missing in?
I don't know. We can talk about it offline. I'm not. Yeah.
Is there some advantage to the dead drop system over passing just onion routed messages in rounds? Isaac Sheff, Cornell.
So we are passing onion routed. So the Mixnet is using onion encryption to enforce the chain and to ensure that the messages are shuffled. But the dead drop ID is just what we came up with that reduces the amount of metadata from the very beginning. So our approach was to eliminate as much metadata as possible from the very beginning and reduce the amount of observable variables that the adversary could see to just very few things. And we reduced it to the 2 things that we saw, which is namely the access counts, the number of dead drops with 1 access and the number of dead drops with 2 accesses. And the dead drops basically were a really convenient primitive that allowed us to hide all the other metadata right away. Yeah.
Hi, I'm from the Joseph, and I'm Joseph, and I'm from the Georgia Tech. I have a question about from the paper discussed about the Vuvuzela does not guarantee the group messaging system, but in case of the end-to-end, if you compute the order combination of the end-to-end, in case of the dialing protocol is guaranteed, then wouldn't it be possible to figure out which subset of the superset is in the conversation?
Could you repeat the question?
Oh, okay. So from the paper, you pretty much discussed that the Vuvuzela does not guarantee, I have no idea what's wrong with the mic. But the Vuvuzela does not guarantee the group messaging system case, right? Vuvuzela only guarantees to the one-to-one, but not end-to-end. It's in the limitation, the section of the 7, the page is 7.
It doesn't guarantee what?
It doesn't guarantee group messaging system.
Oh, right. Okay, yeah. So
Right.
here we only we give guarantees for single-party communication. So an adversary might be able to infer something about the group that you're talking to, but it still won't learn who you're actually talking to specifically. It might be able to infer that you're part of some larger group, but otherwise.
Right. So you kind of assume that entry can be also compromised in a case of the attack, malicious attack. Then as long as the Lazar protocol is preserved, suppose Alice and Bob are continuously exchanging messages, then wouldn't it be possible to having a subset, say there are n users and eliminating n minus 2 users continuously, wouldn't it be possible to find the subset of the superset? In that case, that reveals the Alice and Bob.
So you're assuming that every other, so we assume that all other users are malicious. So in some sense, right, if the adversary sees that only Alice and Bob are the only two real users connected to the system, then right, it can maybe infer that Alice and Bob are maybe talking to each other, but the adversary still won't have definitive proof that it's Alice and Bob talking to each other. For example, they might just be the only two clients that are idle and connected to the system, but there's no way for the adversary to actually learn whether they're actually talking to each other.
Okay, thank you.
Thanks.